And get started. So, what is Python Gurobi? In short, it's a mathematical optimization solver tool or library that will help us to kind of solve mixed integer or linear problems as well as quadratic mathematical optimization problems as well. We can run Python Gurobi in several platforms. The mostly people use is an Anaconda package in either Spider or Jupyter, but if you want, you can also run it in a Java platform, in C++, or MATLAB, and so on and so forth. Gurobi Optimizer is currently considered as the world's fastest solver in terms of approaching complex business challenges and also in terms of solving large-scale network modeling problems. So a lot of big companies like Walmart, Facebook, Google, as well as Home Depot, they use Gurobi and Simplex model pretty often to address the changing business requirements as well as to solve large scale problems in a long term manner. And the reason that a lot of people prefer Python Gurobi over different software packages out there is the superior flexibility that it can offer. So business challenges can change uh, time to time, and then new business challenges emerge, and then you need to always adjust your network model accordingly. It's not a static version that we can use for long-term business planning projections. So whenever it comes to forecasting or long-term planning, using this kind of solver tool like Python Gurobi or Simplex is really helpful. So let's dive into a little bit about some of the basics of a mathematical optimization model. A mathematical optimization model is basically a representation of mathematics, state-of-the-art mathematics that we can use in Gurobi Optimizer to solve real-life supply chain analytics problems or any other operations research problems, in addition to the leverage of computer science. And when we create a mathematical optimization model, there are usually five elements. These are enlisted as here: decision variables, objective function, constraints, coefficients, sets and subscripts. So since the environment that we are used to work in transportation insight, we used supply chain strategies. So some of the information here might seem familiar, like objective function or constraints. But how do they look like in a mathematical optimization model? We'll take a look shortly. So we'll start taking a look at a very simple, straightforward problem in supply chain that is called an assignment problem. This is an integer programming model, which means that it's a linear function with linear constraints using integer variables, and it'll be more easier to understand once we dive into the model itself. So let's take a look at some of these elements that we usually use. So the very first row in a model is called the objective function. It usually has components associated with it, like parameters or coefficients, and it also has a decision variables. So the decision variable is what you are going to get in terms of output when you solve the model. And the decision variables can be either binary variables, like it can hold values 0 to 1, or it can be a continuous variables, like it can hold any value in the real number world, or it can be some other number format that you want to introduce. These symbols, the sum, these are called aggregate sum operators. It actually combines or adds all the values from possible combinations that you want to introduce in your objective function. And we also use similar kind of symbols in constraints. Again, if it seems a bit more technical, then it'll be more understandable in the later part of this session. These highlighted boxes are called data coefficients, or sometimes also called as parameters. This means that the user would provide this value. For example, the problem that we are addressing here is we have a set of jobs which are called J, and then we have a number of people. I'm sorry, there's some spelling mistake here. So number of jobs would be J, and number of people would be I. And then we have a job perfection score, which is called the CIJ, that we want to maximize through our problem. So in such problems, this maximizing these scores of job matching will be provided by the user. For example, if the value for I is 1 and we're looking for a first job, so that means C1 would have a value, let's say, of 5. And then for other 100 different combinations, it can have different values. So that's the user would provide as a parameter or coefficients. Then we have the other rows of this model. These are called constraints. So what the constraint mean is it restricts your business objective, or in what scenario on reality you might be able to operate. So for our problem, since we have an objective function that we want to maximize a total matching score, but we have several constraints. First of all, we are saying that one person can be assigned to each job. So let's say if we have 10 different jobs with the indices j, and if we have 10 people, then for the very first job, only one person would be able to do it. And for all other 9 different combinations, this value would hold 0. So that's why when we sum over the decision variable xij, that means for one particular job, if there are 10% available, only one person would be available to do this job, and then the rest of the 9 combination would not be able to do it. So that's why the summation could be either 0 or at best 1. Similar thing goes for the second constraint. One job can be assigned to each person. So if there is one person and there are 10 different jobs available, only one person can do one particular job. So both of the constraints kind of operate in a similar manner. And finally, we have the range of values that the decision variable can hold. As you can see, the decision variable xij can hold either the value of 0 and 1. That means for a particular combination, they can have a job assigned or not. So since we only have 0 or 1, that means it's a binary values. So that's why this model is called integer programming model. So an integer programming model will always have integer values and mostly like binary variables that it can hold. Some other elements of the mathematical optimization model is the constraint operators. This should be pretty familiar as we use some other software platforms already. Greater than or less than of certain values. And then finally, we have for all operators. What does that mean is we have these index sets and we have the subscripts. So in this index sets contains all the possible value that one particular index can introduce. So if we have 10 jobs available, that means the index set would have 10 different values, and then the lowercase j would contain any value from 1 to 10. So that's why the for all operators refer to that lowercase j can be any element from the uppercase j index set. That's pretty much all of the basic elements that we cover in our basic mathematical optimization model. If you have any questions, feel free to ask and we can talk about that.
I think it seems pretty good. You're breaking out things I haven't seen since college, but
Yeah, most of the things are from college knowledge actually.
Yeah, this was just reminding me my stat classes when I used to take all these alien symbols.
Yep, bringing back the memories.
Yep. Yep. So if there's no question, then we'll move forward to Python Gurobi.
Yes, sir.
So we can pretty much construct several different types of mathematical optimizer model using Python Gurobi. Can be linear programming would be one of the easiest versions of mathematical model that we can build, and then as in increasing difficulties, we can do nonlinear programming, mixed integer linear programming, or mixed integer programming. So those might be some of the fields that you can further explore when we complete this session. So let's take a look at a very simple Python Gurobi modeling example. The reason that we need to learn about mathematical optimization model is the Python Gurobi kind of reflects how you create or develop your mathematical optimization model. So you see here we have an MO with an objective function that we want to maximize a very simple equation, which is x plus y plus 2z. So we have three different variables. So we introduce those variables at the very beginning of this model, and we create this model as MIP1. And in order for us to move ahead with this Python Jupyter example, we import the main library as it's called Gurobi Pi as GP. And then from Gurobi Pi, we always import another function. It's called GRB. So GRB introduces a lot of different functions. For example, here when we introduce these variables x, y, z, as you can see that the variable type is introduced as grb.binary. So that's how we are forcing the model to only contain variables that can hold binary values. And that's why it is called an integer programming model, because we're forcing the variables to contain the value either 0 or 1. And then we set out the objective according to the objective function in the MO. So this is a very simple syntax that we always use as model.setObjective. And then after writing the function that we want to implement, what kind of objective we have. If you have minimize, you'll have grb.minimize or maximize accordingly. And then finally, when we have the constraints, then we add the constraint add model.addConstraint command. And then you can also name your constraint as you wish. This and you can also incorporate several other commands for Python Gurobi. There are a list of commands that you can find on the Gurobi website. And all of the examples that we'll be talking today are mostly reflected on the Gurobi website itself. So if you want to explore further, you can just take a look and dig deep. And then the final command for this model would be model.optimize. So some of the elements that we covered here is how we can import the Gurobi Pi library and how we can use it, introducing our model name, introducing the variable types, as well as the variable, setting up the objective function, constraints, and then run the model. These are the basic elements of Python Gurobi modeling. Any questions on this part?
Hey, Shed, is the I guess the Gurobi Pi, is that like a free open source, or you have to pay for that? It's paid, right?
It's paid, yeah. So yeah, okay. When I was in TI, I was using my academic license, but halfway through my tenure, I think I participated in few of their sessions, so they rewarded me with a 2-year-long subscription. So I think that's something that can be potential avenue to explore. Like if you are able to participate in several Gurobi sessions, you can reach out to the admin forum, and then you can request like whether would it be possible to get a free license for a certain time period. But I think you can also get license as an institution, and it's not that expensive.
Okay, that's fine. Yeah, just wondering. I was like, I thought Gurobi cost, but I didn't know if they had any free like open source or anything like that. But I'm sure once you pay for it, you can access all of it.
Yeah,
I think the price is not that expensive, Jeremy. Plus, they offer a host of other features. And this is my reason for us to explore this is once we gain mastery on this, we can do a lot more than what we are doing right now with some of these tools that we are using.
Mm-hmm. Yeah, it's pretty powerful.
Yeah, and also I think if you request, they also allow a certain time period that you can access free trial. That can be, if that's been requested from an organizational perspective, they might allow, I guess, 1 or 2 months of free access, and then you can run it on a trial basis.
Gotcha. Yep. All right, cool. Makes sense.
Okay, so if we don't have any other questions, so let's actually deep dive in one of the full-fledged problem using Python Gurobi. The first use case would be a beginner level complexity, meaning that we have some knowledge of Python and we know how to build a mathematical optimization model. So the facility location problem is should be pretty familiar with most of us. Uh, we have a set of customers and we have a set of candidate warehouse locations. As in this case, it's considered to be in northern England. So we have two supermarkets that we want to serve, and we have 9 potential warehouse candidate locations. So we want to find how many warehouses we can build optimally. Um, we can open as many warehouses as we want. That would be advantageous in order for us to reduce the maximum weighted average distance to our customers, but as well as it also incur a certain amount of associated fixed opening cost for a particular facility. So let's take a look like how we can formulate this problem into a mathematical optimization and then eventually create a Gurobi model. So this is a very simple data structure. We have 2 different customers, which is the 2 different supermarkets with their coordinates. And we have 9 potential warehouse locations with their coordinates as well as their fixed establishment cost. In terms of material delivery, we have the cost per mile is 1 billion GBP. That means like if we want to have demand transfer from warehouse to supermarket, what would be the cost of that in association with the fixed cost? So we first introduce the sets and then parameters, and finally with the decision variables. So we have 2 different sets. One, we have customer set, which is introduced with the uppercase I. And then we have the set of candidate warehouse, which is the uppercase J. Parameters are the set of given values by the user to the input model. So we have Fj, which translates into the fixed cost associated with any facility construction. That would be any element from the uppercase J. Then we have the distance from customer to warehouse, which is the Dij. And then we have the cost of shipping as well from a particular warehouse to a particular customer, which happen to be the supermarket. And in this problem, we consider the cost is proportional to the distance between the facility and customer. So since we know that the cost per mile is 1 billion Great Britain pound, so if we can find the distances between one warehouse and one supermarket, we just multiply it with the cost per mile to get the cost of shipping between candidate facility and a customer location. And then finally, we introduce the decision variable. We have the select variable, which is binary. It can hold either the value 0 or 1. 1 if we build a facility at a candidate location from the element uppercase J, and if not, then it would be 0 otherwise. And then we have another variable which is called assign. So this assign would be, it is introduced as a non-negative continuous variable. So with non-negative, what it means is since it determines the fraction of the supply that would be received by the customer or the supermarket, so it can hold the entire value of the demand or it can be a fraction of the demand. That's why it is introduced as a non-negative continuous variable. So when we explain the concept, it will be more clear to understand. So first of all, we establish the objective function. So our goal is to minimize the total cost to open and operate facilities. So we have 2 different costs. One is opening a new facility, which is the fixed cost would be Fj. So if any particular warehouse we need to open, that would be a select variable, binary. And if it's open, that means you'll get the associated cost to be selected as well. And then if we assign to any existing facilities, then we select which warehouse it is and then which customer it will be shipping to. So that's why, since it's a combination of a parameter and a decision variable, that's why it is considered as a dual sum. For constraints, the first constraint is assuming that whenever we assign a warehouse to a customer or as well as the supermarket, we're assuming that that particular warehouse would satisfy the entire demand for the supermarket, meaning that the supermarket will have its entire demand fulfilled by one particular warehouse and not two. So that's why the summation of this assignment is 1. In a situation where we would like our assignments to be splitted in between different warehouses, in that case this constraint would be nullified and we'll have to introduce it in a different manner, and we'll introduce that in the use case 2. And then finally we have shipping constraint. So we need to ensure that we only ship from one facility. So since there are 9 potential facility, but we can only assign for one supermarket, we can only assign one warehouse. So we want to make sure that those value is either equals or less than all the select values that it can hold. Any questions?
No, guys, please continue.
Okay. Okay, so we'll go ahead and start building the mathematical model. So here we are importing 3 different libraries. First one we can import is the Gurobi as well as the Gurobi function. And then we also introduce 2 different functions, one the iter tools, in order for us to develop logics inside the model, as well as the math function to import certain features for calculated distances. So since we know that we have this data available to use for us in the model, so what we do is we initiate this or introduce this parameter into different dictionaries. We have 4 different dictionaries here. We have customers and their coordinates. We have the facilities as well as their fixed cost. And then we have the setup cost. And then we also introduce the cost per mile equals to 1 because that's 1 million GBP. Moving forward, we do some pre-processing of the data. This is very straightforward. We're computing the distance. So in this example, we're saying that the Euclidean distance is calculated. In TI, we always do haversine distances, so you can just pretty much incorporate that formula and kind of redo this function as compute distance within 2 different locations. We also introduce some of the other parameters, number of facilities, number of customers, and also do a Cartesian product to get all the possible combinations. So since we have 2 supermarkets and 9 different warehouse candidate locations, so in that case we'll have 18 different possible combinations. And then finally we have the shipping costs. The shipping cost would be considered in a logic using the cost and the warehouse functions. And then finally we create the model. So we already know how the model is structured. So we name our model as facility location. We introduce 2 of our variables, which is the select variable and the assign variable. So as we have mentioned before from the model, that our select variable would be binary, meaning that we can select a facility or not. So it can either hold the value 0 or 1. So that's why it's a binary variable. And then in terms of demand, we have an assigned variable which is continuous. So that's why this is a different variable type. And since we are using 2 different variable types, that's why this problem is called a mixed integer problem or an MIP model. So the basic difference between LP model versus an MIP model is in LP model, you'll all have the same type of variables, either binary or either continuous. And in an NIP model, you'll have a combination of different variables. So after introducing the variables, we introduce the constraints. And as you can see, we are using a for loop. so that every possible combination is accounted for. And finally, we set out our objective that we want to have the select production cost as well as assign select setup cost as well as assign shipping cost, and we want to overall minimize the objective function. And then finally, we run the command, which is the optimize function. The user output or the model output is something similar to this, what we have here. Um, there are some elements that is very interesting, as we can see here, is as you take a look at this particular line, variable types, there are a total of 18 continuous variables. So since we have 18 different combinations, that's why 18 different variable types are considered as continuous. Since we have 9 different facilities that can be either selected or not, so that's why we have 9 integer variables or 9 binary variables. So these are some of the key aspects that you can double check when you run a model to ensure that your model inputs has been captured properly. And if you see that it does not resonate with the model that you have built, so that means you'll know that there's something wrong with the model build or how you have written it in the Python Gurobi model. And then another interesting observation in this output is the gap percentage. The reason that is very important is it will tell you how robust is your model and how robust you have created it in your Python Gurobi modeling workbook. So we have objective incumbent and bench bounds, and the difference is objective incumbent refers to whatever model you have created. This is the best possible reason that the model can output. Excuse me. And the best bound is considered as considering the upper bound and lower bound of this particular model, what's the best option that it can achieve. And when you have a 0% gap in between these two options, you know that the model is very strictly knitted and that all the data inputs and the model are in well conjunction with each other. For your modeling purpose, you can play around with this gap percentage, and when we'll be working in a large scale network modeling, we can eventually introduce this gap percentage as a parameter. So kind of set a threshold. What is the tolerance limit that you can accept? So this entirely depends on your business objective, like how much tolerance you can achieve in your business objective, how much tolerance uh, you can have in your savings dollars amount or your service level. So that's a very important element in the output to consider. So as you can see that the model says we have an optimal solution found. We have a best objective value of 4.72. That means the optimal model shows the minimum total cost that we can achieve using this model is 4.72 Great Britain pound, with the best gap percentage 0.00%. So this is the absolute result that we can achieve using this mathematical optimization model and the Gurobi. So finally, we can take a look at how this devises the warehouse optimal location plan. So we have the warehouse build plan as well as the shipment plan using a logics here. So as you can see, it says we will build a warehouse in location 4, and then both of the supermarkets or customers would receive it demands from that particular warehouse. So one very interesting observation here is if you look at these results, it says 100% of his demand would be from warehouse 4. That eventually is the result of our first constraint here, that we are forcing whatever warehouse we select is going to serve the entire demand for that particular customer. For this particular constraint not have been taken into place, then we might have seen splitted demand in between different warehouses. That's something we're going to experience, we're going to see in the second use case. Any questions for the first user case or I can help clarify with.
Nothing on my end.
Okay.
No, seems pretty applicable with what we're doing with the network design here, so that makes sense.
So, Zach, Mike, I was trying to put a question for you as well while on mute. So, for you and Jeremy, I wanted to make sure can because you guys are closest to in our area to work on these problems. Are you guys able to relate this to the work you guys have been doing?
Yeah, I mean, for the most part, this framework, we have the Cartesian here, which is the combination. So that's kind of like the lanes. This is for miles, so we would just have to, put in lane cost to get it down to the lane cost.
Yeah.
Use the Haber for miles, but I think mostly, I see everything here and it seems to make sense. Yeah.
Yeah, and as we make progress to the next use case, that's a little more involved, and I think that will make a little bit more sense and kind of help us dive deep into how we can better relate to one of the projects or some of the projects that we've been doing recently, or any of the future projects that we want to explore. So moving onward to second use case, which is capacity planning, and this is considered as a medium complexity level, which would mean that we have a good knowledge of Python, and now we know how to build mathematical optimization models. So this is COVID facility capacity optimization problem. Um, our business challenge here is we have 9 different counties with 14 existing locations and 9 possible candidate temporary locations. Our business problem is currently these counties are suffering from capacity issues, meaning that they don't have enough beds or places to go for COVID treatment. So we want to know how we can better assign patients across these different locations, as well as whether there is need to establish new facilities and what will be the cost associated with it. So this example, our goal is to identify how we can better accommodate the demand for treatment, how we can best utilize the overall capacity, and how those counties would be allocated to different healthcare facilities to provide better treatment for patients. And I think the way we can relate it to a supply chain problem is pretty much common in terms if one of our client has stores and different warehouses, uh, how they can better serve in terms of capacity to meet the demands for each of the stores, or whether there is any increasing need for any particular store growth in future or in long-term growth. So this would be an MIP model, and now that we know how a MIP model is formulated, so I think it would be easier for us to follow. These are some of the data elements that would be input into the model. Very straightforward. We have the first table shows how many counties do we have, their coordinates, as well as associated demand. The second table is all of the existing facilities that we have with their coordinates and their current capacity. And finally, we have the temporary potential candidate locations with their coordinates and capacity. As you can see, that building a temporary location would cost around $500,000 with an additional 100 capacity. And at the very beginning, we can see that the cost is considered, driving cost is considered at 10 miles, which is $5. So for every 10 miles, we increase a $5 transportation cost for each COVID patient to travel from a county to any particular facility. So let's take a look at how we create the mathematical model. First, again, we introduce with sets and indices. So we have a set for all the existing healthcare facility locations, and we have another set for temporary healthcare locations. And then we do a union to get all the possible set of locations. And then we have another set for counties. For parameters, we have the distances between counties and each facility location. We have the demographics where it says how many people are there in one county that needs a COVID facility in terms of demand. We have the capacity for each facility. Driving cost is again $5 for every 10 miles, and then temporary fixed cost is 500,000 for any temporary facility location that we plan to establish. And then finally, we have another penalty, which is called, in terms of adding extra capacity at temporary facility. The reason that we are using this penalty is we don't want to create, or we are reluctant to create a temporary facility unless it comes to an absolute necessity. So that's how we force the model to allocate as much and as best as possible to all the demands to an existing facility. And finally, we have the decision variables. Again, if we have temporary facility, if a temporary or a new location is selected, then the value would hold 1, otherwise 0. So this is a binary variable. We have number of people from a particular county that would be served by a particular location. So this is very interesting in a sense, and compared to the first use case is, let's say if we have Catawba County here in Hickory, and it can be served by 2 or 3 different facilities. So we know that one particular county will not be able to be supported by one particular facility. Instead, it will be served by multiple facilities. That's why it is called a continuous variable, meaning the demand would be split in different, according to different facilities that we consider. And then finally, we have another variable, decision variable, which is called ZT. It is for the extra capacity that will be added to a temporal facility location. Any questions on this slide?
Nope.
So
Does it since 2 facilities are servicing one county, does it decide it would probably be serviced by the cheaper facility first, and then when it hits capacity, then the next one comes into play? Is that kind of how it does it?
so I think the objective function will better answer this question. So if we look at the objective function, that's how we determine like what it's gonna do. So in our objective function, what we are trying to do is we have a particular sum function where we want to minimize the transfer cost from one particular county to an existing facility. That's the first part of the objective function. Then we have the second part, which is the fixed cost. And then finally, we have the penalty. So all of these are woven together to this objective function, and we want to minimize the entire function. So that means it will try to look all the possible combination it can have, looking at the transfer cost from one county to existing facilities, as well as all the possible temporary facility opening costs that it can incur, and all the possible combination in terms of demand allocation. So Gurobi will keep assessing each of these scenarios and then will provide the final optimal solution. And the reason that we use the penalty function here is we are forcing the model to allocate as much demand as possible to the existing facilities, and kind of avoid any potential cost that it can incur from setting up a new facility. Does that help answer your question, Zach?
Yep.
Okay.
Thanks.
Yep. So Our first constraint is all about demand satisfaction. This is very much comparable to our first use case where we had all the demand satisfied by one warehouse location. Here we are saying that for a particular county demand for COVID-19 patients, it will be served by multiple different facilities. So that's why it's a continuous variable summed over. We have an existing facilities constraint, which is very straightforward, that an existing location's capacity cannot be exceeded from the given values. And then we also have a temporary facilities capacity that it also cannot exist from a given value. And one thing to notice in this constraint that we can see that extra capacity can still be added. That's how it's associated with the penalty factor. So if as a last resort the objective function deems it to be appropriate to establish a new temporary facility, in that case the constraint will satisfy that requirement. So we go ahead and start creating our Python model. First, we install the Gurobi library and import all our necessary functions, Gurobi as well as math function and other tools. Again, you can use the Haversine formulas to kind of calculate the distance in between different locations or two different coordinates. Then we create another function to kind of account for the coordinates, since we have a larger table. So we create these lists to account for all the possible values. Here we keep continuing to develop the logics to create all the possible combinations that we can get, and also introducing the parameter values for transfer cost as well as the total fixed cost. And finally, we start creating the model. So as we are saying here is we have the model as COVID-19 temporary facility location. That's our name. We introduce three variables. Two of them are continuous, and the first one is binary. So again, since we have a mixture of different variable types, that's why we're calling this problem as an MIP model. We also introduce the big penalty, which is a really big number that again forcing the objective function to kind of accommodate as much as it can to accommodate the demands across existing facilities. Our objective function is to minimize, and then we add all the constraints for our model using the for loops. And finally, we run the optimization engine. Next, we take a look at the optimization result. We see the model says optimal solution found at 1.52, meaning that the optimal cost would be $1.52 million. And then the optimal cost also shows the cost breakdown for existing facilities as well as new facilities to be open. So in terms of new facility establishment costs, that would be 1.5 million. So we know that each facility would require 500,000 additional costs. So that means 3 new facilities is being considered to establish as a temporary facility. As you can see, those are 3 different locations, 15, 17, 18, among all the 9 possible locations provided. And then we have the total cost for transferring patients to an existing facility, which is 21,645. And then we see part of the result shows here is how these county's patients are allocated to different facilities. If you look at row 3 of these results, you see the county 3 demands are being distributed to 2 different facilities, which is facility 3 and 4. So that's why this variable was considered continuous in the first place, because it can incur any value based on the optimization would be run. So you can tailor the output as you want. You can break it down to more granular level to kind of show the associated cost for each of these combination, and kind of do scenarios as you deem appropriate. Any questions on this second use case? Okay. If not, I think that pretty much concludes our session. Hope I've not been very fast forward in terms of discussing, so apologize if I've done any. But based on this session, some of the future avenues that we can explore is how we can leverage large scale data input based on our project scope, and how we can leverage SQL or cloud for data input purposes. There are plenty of resources in the website mentioned here. And also, object-oriented programming might be a very good field to explore, uh, given you want to move further with Gurobi modeling. Uh, that's something I use a lot. That is very handy if you want to build a large scale network modeling, in a sense that you'll have superior flexibility in terms of data input, in terms of data modeling or object building, and you can add as many elements as you want based on your changing business requirements. Complex network modeling examples from the Gurobi website might be another potential avenues to explore to kind of get more in-depth insight on data input and logic building. And finally, you can also, and definitely a must to do, is how to better report these results, and also whether you can create direct visualization using Gurobi with leveraging the Matplotlib or any other fancy library that you can use. Um, so those are some of the things I think would be really interesting for all of us to kind of continue exploring. And here I have provided the first two references are the model that I have discussed today. These are all from Python Gurobi. I felt that it would be really interesting if you want to dig deep, but I've tried to cover as much as I can. I've also provided the link to these optimization models. Feel free to copy and run in Colab, Google Colab, or you can also download the problem and run in your own Jupyter notebook. Also provided the link for Python Groove installation, as well as a lot of examples that is available on this link. So feel free to explore, and I think that would be really helpful. Yep. So that pretty much concludes our session. Happy to answer any questions or concerns you all might have.
So I will start with my question. So you have used Gurobi in this, which seems to be one of I think Gurobi and Simplex are kind of neck-to-neck competition in optimization solvers.
Yes. So Gurobi and Cplex are pretty similar in terms of language or model building.
Mm-hmm.
The reason I talk mostly about Gurobi and not Cplex is I think Gurobi would be a very interesting and easier to follow library compared with
Mm-hmm.
Cplex, because Cplex is an older version. So
Uh,
Gurobi would be much more faster and easier to approach, and the languages are pretty easy as well as the functions and commands.
what about something called as pulp?
Pulp would be something really interesting, but I would highly recommend to get someone familiarized first with the concepts of Gurobi or the mathematical optimization modeling.
Mm-hmm.
Once having pretty much a good background, then it would be easier to follow the pulp functions. Those are more straightforward, but some of the features might be a little bit tricky and would require some in-depth knowledge beforehand. But pulp is definitely a much better version to
Is
explore.
it?
Yeah, and one more addition would be pulp is still being innovated. on a frequent manner. So
Mhm.
while building some small or little models would be feasible, but in
Mhm.
the case of building large scale models, there would be I fear that there will be little to no resource available because it's really still being researched. So not
Got
a
it.
lot
Okay.
of large scale problems would be available for exploration.
Got it. Okay. Thank you. Guys, any questions you have for Shahid?
I don't. Thanks ahead.
All good on my side.
Cool. So my thing for you guys is, do you guys see more possibilities with this of what all can be done? Like again, this is what Shahid has shared is just a scratch on the surface of what we can do in optimization. But my goal of this meeting was to see if you guys can see the light that can come out by exploring this option.
Yeah, I
Yeah,
mean, I can.
I think there's definitely some opportunity here, or at least I would like to start looking into it a little more. I think this is kind of like the direction we're trying to head into things. So yeah, 100%.
The way I see Alex is the market and the industry is changing a lot. And personally, if you guys can, learn these skills, what Shahid has learned and has shared, this will be a great value add because all these, off-the-shelf programs, they offer good features, but they are expensive, they are limited to some extent. But if you learn these, then your, possibility of running complex problems or customized problems is very much possible by utilizing these tools. So that was the goal. I hope you guys at least see a starter or kinker, to see that these things are possible. Shayad has shared the links. Shayad, would it be possible for you to share this PowerPoint too, sir?
Yes, absolutely. I'll email it to you all so that you can take a look later on.
Yeah, if you can please share it, then the team can look into it.
Absolutely.
Oh, anyone else has any questions, comments?
Jahad, do you use this at Home Depot or do you do other things?
I mostly use Ciplex for my current workplace and some of the long-term network modeling that I've deployed recently. Um, so I think that would be a really interesting for all of us to kind of continue exploring, as or Sajjan has already mentioned that the kind of platform that we use, either it can be Strategist or Lamasoft or any other platforms, they do have certain limitations in terms of data reporting, and you'll have to know your way around, like when you build a large model. But once you get yourself familiarized with these libraries and models, it at first it might seem a little bit more technical, but might take a month or two to get yourself fully familiarized. And once you do that, it just opens up endless possibilities and just you know like open up all the possible fields that you can explore. And also, what I feel really important would be the type of work that we do at Transportation Insight is kind of offer more than what the client asks. So that will certainly open up doors for a lot of possibilities. So highly recommend to explore this further, and always feel free to let me know if I can be any further help.
So, Shad, one other question at Home Depot, what what kind of projects you guys use? Uh, you use like tools like Lamasoft and all those things, and what kind of projects you use these open technologies?
So in our like supply chain organization, we have some tools available to most of the analysts or researchers. One that we use is IBM LogicNet Plus, which is really good, kind of similar to what we do, what we have used in strategies.
Uh-huh.
But a lot of the teams use Python Cplex and Gurobi.
Mm-hmm.
And in my role, I kind of serve as an operations researcher to kind of explore and also kind of modify the existing business problems. And the one that I recently deployed is a long-term network model for one of Home Depot supply chain that would incorporate vendors like all around the world, like around 500 different vendors, and then there are 5 or 6 different shipping ports that we use, and then in terms of warehouse, we have like 140 different warehouses that we incorporated in this analysis, and then stores like 2,000, more than 2,000 stores nationwide. So the type of business problem it was kind of introducing new transportation mode to the supply chain, both at a vendor level as well as to the outbound level. And one of the main business challenge was that when we introduce a new transportation mode, that particular transportation mode would have different types of capacity or mode itself. For example, when we talk about truck, it can be a flat truck, it can be a container truck, or it can be a small truck. So think of it this way: that one particular mode can have 3 different capacity issues, as well as we also used SKUs. So there are like 1.5 billion SKUs, and all these SKUs have different restrictions for warehouses as well as stores. And also at SKU level, some of these SKUs has capacity as well as delivery limit, capacity in terms of vendor as well as delivery in terms of stores. So kind of when you deal with that large number of SKU combinations as well as store warehouse, it's very flexible using Gurobi that you can work on the general level.
That makes sense. Cool. Any questions for Shahid, guys? Shahid, thanks again, man. This was very helpful and very interesting, and I hope team gets some motivation from this, and we start exploring it. And once we start exploring, we'll come back to you again for more guidance. But
Sure.
truly appreciate it. Thanks a lot for this.
Yep, no problem. Thank you so much, guys. Nice talking to you.
Appreciate it. Yeah,
Thank
thank you.
Thank you.
Thank you.
Great.
Shit.
Thank you guys.
Thank you.
Thank you. Bye.